All right, so ready to dive into some algebra.
Always up for a little mathematical deep dive.
This time it's an algebra refresh, and we're going way beyond just, the basic formulas. We've got excerpts from a textbook chapter on algebraic expressions and identities.
Sounds like a trip back to high school math class.
Well, hold on, because we're not aiming to relive those memories. This is about rediscovering the beauty and, dare I say, the fun of algebra.
I like where you're going with this. It's about those aha moments where things click into place.
Exactly. So we're starting with the fundamentals, those building blocks of algebra. Algebraic expressions.
Right, and our source material starts with, like, some pretty simple examples.
Yeah.
X plus 3, 2y5, the basics.
Right. But even in these simple expressions, there's a lot more going on than meets the eye. Like when we see x3, it's not just about adding 3 to some random number. That x is like a key that unlocks a world of possibilities.
Absolutely. It's a variable. It's saying, hey, this value could be anything, any number you can dream up.
And that's where it gets interesting. Our source material talks about how the value of an expression changes based on what you plug in for that variable.
Right, like picture x on a number line. Say x starts at 2. So x3 would land you on 5, right?
Yeah.
But if you slide x over to -1, suddenly x33 puts you at 2 on that same line.
It's like the whole expression is shifting and moving based on that one variable.
Exactly. And that's the dynamic nature of algebraic expressions. Change the input, change the output.
Okay, so we've got these expressions, they're dynamic, they can change, but how do we make sense of their individual parts? Because I'll admit, terms like terms, factors, coefficients, those always kind of blurred together in my mind.
Yeah, it can feel like a jumble of jargon. Let's use your example from earlier, 2y5. See how it has those two distinct parts separated by the minus sign?
Yeah, so two separate chunks.
Exactly. Those chunks, those are your terms. They're like the building blocks of the expression.
Okay, so if we think of an expression like a sentence, the terms are like the individual words.
Perfect analogy. Now zoom in on one of those terms, like 2y. You've got the 2 and the y hanging out together and they're being multiplied. Those are your factors.
So factors are like the letters within the words of our sentence.
I like it. And that numerical factor, the 2 and y in this case, that's our coefficient.
So what's so special about that too? What's its role?
Think of it this way. The coefficient tells you how many of that variable you're working with. In 2y, you've got 2 y's essentially being added together. It's a subtle distinction, but it becomes important as things get more, shall we say, interesting. So we've got these expressions all broken down.
You know their parts.
Now, how do we actually group them, like classify them?
Our source material mentions these terms, monomials, binomials, and polynomials.
Yes, the classics.
Yeah.
Bringing back memories.
Vaguely. Like, I remember them being different levels of complexity or something. Monomials being the simplest.
Exactly. Monomials are the simplest type of algebraic expression. They have just one term.
One term. Simple enough. And our source material gives an example. 4 by Lesant. That would be a monomial, right?
Perfect example. Now, take a little step up, and you've got your binomials, 2 terms.
So our trusty example from earlier, 2y5, that would qualify as a binomial.
It certainly would. And then anything beyond 2 terms, we enter the realm of polynomials. A plus B plus C, even something a bit more involved like 2x, 3y5. Those are all polynomials.
Okay, so it's like a hierarchy of expressions, monomials at the bottom, then binomials, then polynomials at the top.
A very organized hierarchy.
And speaking of organization, our source material dives into these concepts of like and unlike terms. Is this where algebra gets judgmental?
Not quite. Like, terms in algebra simply have the same variables raised to the same power. The coefficient, that number out in front, can be different.
So like 7x and any 13x would be considered like, even though one's positive and one's negative?
Exactly. They both share that x to the first power. But 7x and 7 side, those would be unlike, because the variables are different. And even something like 7x and 5x side, those are unlike as well, because the powers of x don't match up.
So x and x had different powers, different teams. Okay, that makes sense. But why is this distinction so important? It's not just about keeping things tidy, right?
Right. Not at all. It's crucial for when we want to actually do things with these expressions. Like add, subtract, multiply. It's all about combining what can actually be combined.
Like you can't add apples and oranges and get some kind of superfruit.
Exactly.
So you can only combine like terms. That makes sense. Our source material actually gives a good example. 3x, 2y, 5xy.
Right, so you would combine those x terms separately from those y terms.
So 3 by 5x, that gives us next 2x, and then 2yu would be 3y.
Precisely.
Leaving us with a nice and tidy 9 to 2x, 3y. That's pretty straightforward when you lay it out like that.
And things can get even more exciting when we step up our game and start talking about multiplication.
Multiplication, now we're talking. Does multiplication care about those like and unlike terms?
Multiplication has its own set of rules.
Oh boy, more rules.
Let's start simple. Multiplying monomials. So something like 2 by 3y. It's basically just multiplying the coefficients together and then the variables.
So that would be 2 times 3 times x times y, which gives us 6, 1. See, I remember something.
And that's the beauty of it. It builds on what you already know. Now, how about multiplying a monomial by a polynomial? Say 3x, 4x2. Think of it like this. That 3x needs to shake hands with each term inside those parentheses.
So each term in the parentheses gets its own little meet and greet with the 3x. So we'd have 3x times 4x plus 3x times 2.
Exactly.
Which simplifies to 12x of 6x.
Now you're getting it. But are you ready for the real challenge?
Bring it on.
Multiplying two polynomials. Let's say x2 times 2 by 1.
Okay, I can feel the complexity already.
It's really just about systematic organization.
Organization, I can do that, I think.
So we need to make sure that every term in that first set of parentheses, the x2, gets a chance to multiply with every term in that second set of parentheses, the 2 by 1.
So the x from x2 needs to interact with both the 2x and the minus 1 from the 2 by 1.
Yes, and then the 2 needs to do the same thing.
Okay, so it's like a square dance where everyone needs to partner up. So we would end up with x times 2x plus x times minus 1 plus 2 times 2x plus 2 times monaigos.
And then you simplify that whole thing down to 2x to 3 by 2, 4.
Right.
You've officially expanded that expression.
It's like we're taking a seemingly complex problem, breaking it down into smaller, manageable steps, and then putting it all back together.
It's a process.
Yeah.
And, this isn't just some abstract mathematical gymnastics. This stuff actually has real-world applications.
Oh, yeah. Like what?
Think about, calculating the area of a rectangle. Let's say the length and width of that rectangle are expressed as binomials.
Okay, so area, that's length times width.
Right. And if those dimensions are represented as binomials, well, you'd need to use this polynomial multiplication to figure out the area.
So in that case, algebra is practically the same thing as geometry.
It's all connected, and this is just the tip of the iceberg.
Algebra in the wild. I like it. Okay, so we've tackled expressions, we've broken them down, we've built them back up. What's next on our algebra adventure?
Our source material throws us a bit of a curveball, introduces this concept of algebraic identities.
Algebraic identities, huh?
Yeah.
So is this where algebra finally has that existential crisis and figures out who it is?
Not quite an existential crisis.
Okay.
But you're on the right track with the figuring things out idea.
Okay, so enlighten me.
So imagine having these, pre-solved equations, these formulas that are always true, no matter what values you decide to plug in for the variables.
So it's like having a cheat sheet for algebra.
Kind of. You see a certain pattern, you can just apply the identity, boom, problem solved.
I like the sound of that. Less work, more algebra magic.
Exactly. And our source material actually dives into 3 specific identities. One of them is ab squared equals a squared plus 2ab plus b squared.
Okay, let me see if I can translate that. So if we take a binomial, like our friend from earlier, and we square it, meaning we multiply it by itself.
Then we end up with a specific pattern on the other side of that equal sign.
And that pattern is a squared plus 2ab plus b squared.
You got it. You square that first term, you add twice the product of both terms, and then you square that last term.
So instead of going through the whole process of actually multiplying it all out, we can just skip ahead to the answer using this identity.
You're catching on. And it's not just about abstract variables either. Our source material gives a great example of trying to square 103. Now, you could do that the long way, but think of it as 103 squared.
Oh, right, because 100 plus 3 is 103.
Exactly. So you can apply this identity and get to that answer much faster than multiplying it out by hand.
That's actually super useful. Why didn't they teach us that in school? Would have saved me a lot of, let's call it creative math on my tests.
Well, now you know. It's all about having the right tools for the job.
So we've got one identity down. What about the other 2 our source material mentions?
Right, so the second one is very similar to the first. ab squared equals a squared minus 2ab plus b squared.
So essentially the same idea as the first one, but with subtraction in the mix.
Exactly. Instead of adding that 2ab term, you're subtracting it.
Okay, so far so good. And the third identity. This one, our source material presents as ab equals a squared minus b squared. That feels a bit different.
It does look a bit trickier, right? But the result is surprisingly simple. Just the difference of those 2 squares.
So we're multiplying the sum and the difference of the same 2 terms. That's a good one to have in your back pocket, I'm realizing.
Absolutely. And speaking of things to have in your back pocket, our source material mentions there's actually a fourth identity.
It does, a fourth, even more general identity, though I noticed it doesn't actually give us the formula.
It's true. It just hints at its existence.
A little algebra mystery for our listeners to ponder.
Exactly.
Well, I'd say this has been a pretty fantastic deep dive. We've gone from those fundamental building blocks of algebraic expressions all the way to these powerful identities, and we've even uncovered a little algebraic enigma to keep those minds engaged. Hopefully this has been a fun refresher for everyone, and hey, maybe even spark some curiosity to explore those hidden depths of algebra a little further. Until next time.